Physics students, good afternoon. Mr. Hughes here. In our video today, we're going to be looking at the second part of our graphical kinematics practice, the velocity versus time graph. And remember, you can access this document directly on Canvas. There is also a key on Canvas if you're looking just for the answers. But here we're going to be walking through the problems, 5 through 10, for the velocity versus time graph. Okay? So we're just going to jump in and get started. Remember, everything we do here is specific to the type of graph we have. This is a velocity versus time graph, which means everything we do has to be under the understanding that this represents velocity versus time. So we'll jump down here. Question number 5 is, what is the velocity of the object at a time of 2 seconds, 5 seconds, and 8 seconds? So here, because our because our graph directly tells us about velocity, all we need to do here is look at our points. So at 2 seconds, I'm at a velocity of 1 meter per second. So I would say at 2 seconds, my velocity is 1 meter per second. Just reading my point directly. At 5 seconds, I'll come over to 5, right between 4 and 6. Looks like I'm at a velocity of 2 meters per second. That is positive because I am above my time axis here. And then at a time of 8 seconds, I'll go 8 seconds. Trace down. Looks like I'm at about negative 2 meters per second. So again, because this is a graph of velocity versus time, that means our velocity is just presented to us directly. Right? If this was a position graph and we were asked for velocity, we would have to find the slope. But here, because our graph is velocity, we can just read those points directly. Okay, so now we'll move on to number 6. And we'll erase our markings. Number 6 says this: when and ever is the object not moving? Well, remember, by definition, velocity measures how fast something is moving. So if an object is not moving, that would mean our velocity equals 0 meters per second. Right? So now, we need to look at our graph to figure out where is our velocity 0 meters per second. So if I come back up to my graph, again, because this tells us directly about the velocity, I just want to find where's my velocity hit 0. So here's where I hit 0. I go along my axis, time axis here, I hit 0 here, and I hit 0 again. Now again, if this were a position graph, we'd be looking for where is our slope 0, because for position versus time, our slope is our velocity. But here, because our graph directly tells us about the velocity, wherever the velocity hits 0, our object would not be moving. So that is at a time of 0 seconds, at 6 seconds, and at 9 seconds. So we would say time is equal to 0, 6, and 9 seconds at those times, or when our object is not moving because our velocity is 0. That would be our explanation. Okay, we'll move on now to number 7. It says, when and ever does the object turn around? I'm going to come back and, oh, no, don't do that. Oh, there we go. Sorry, sometimes the smart board is a little sensitive, as you've seen in class. So, when and ever does the object turn around? Well, by definition, in order for an object to turn around, what has to happen is that our velocity must change sign. Meaning, we have to go from either a positive velocity to a negative velocity, or from a negative velocity to a positive velocity. So it means we move in one direction, we stop, and then we begin moving in the other direction. Or vice versa. We move negative, stop, and then we begin moving positive. Either one of those would represent a change in sign. So we'll come back to our graph of velocity versus time. I'm going to erase my markings here. Now you'll notice from time 0 all the way up to 6 seconds, my velocity is positive. From 6 to 9, my velocity is negative. And then from 9 forward, my velocity is positive. The reason I can tell that is because my line here is above 0. So positive, positive, positive. Again, we're not really concerned with what our velocity is, just what's the sign. And then we have a point here when now it becomes negative, and then another point when it becomes positive. So we're asking, when does the object turn around? That means where specifically does our velocity change sign? And it goes from positive to negative at 6 seconds, and from negative back to positive at 9 seconds. So we would say here, our velocity changes sign at a time of 6 seconds, and at a time of 9 seconds. Now, we don't know what's going on before time 0. right? If I come back to my graph, I don't really know what's happening before this first point in time. So we can't definitively say it changes sign at time 0, because all we know there is that we're stopped. We don't know what we were doing before that time. Okay? As well, what we have to watch is this. Let's say our graph, for example, at 6 seconds, what if we stopped and then we began moving like so? The green line. There, even though I stop, my velocity then goes positive after 6 seconds. That would not be a change in direction. We would not be turning around there, because even though we stop, we then begin moving in the positive direction again. So just because we stop doesn't necessarily mean we're changing direction. Okay? In order for us to turn around or change direction, our velocity has to go from positive to negative or negative to positive. Okay? So hopefully that clarifies 5, 6, and 7. Okay? I'll erase my markings here, and we'll keep moving. Now we'll look down. I believe we'll go to the next page. So we'll look down at number 8. Number 8 says this: what is the acceleration of the object during the time intervals 0 to 1 seconds, 1 to 4, we'll do these in 3 colors, and 5 to 7. So again, because we're dealing with the graph of velocity versus time, in order to find the acceleration, that means we will need to find the slope of the line during those time intervals. So we'll first start with 0 to 1 seconds. I'll come back to my graph. So 0 up to 1. I'll find the slope of my line there. So look at my 2 ending points. So at time 0, I'm at a velocity of 0 meters per second. And at time 1, I'm at a velocity of, I believe, 1 meter per second. Let me double check. Yes. Okay, so the slope between those points, well, my y values are my velocities, so y2 minus y1, 1 minus 0. And x2 minus x1, 1 minus 0. So 1 minus 0 gives me 1 meter per second over 1 second. So 1 divided by 1 just gives me a value of 1 meter per second squared. That would be my acceleration. It's positive because I have a positive slope. It means I changed my velocity 1 meter per second in 1 second, just the slope of our line. Now we're going to look at 1 to 4 seconds. Now, in order to make this a little bit easier, from 1 to 4 seconds, what we should notice is that we have a flat line there, which means our velocity is not changing. By definition, acceleration is the measure of how much our velocity changes, whether we speed up or slow down. And if we're not speeding up or slowing down, that means during that time interval, our acceleration would be 0 meters per second squared. Because we have a flat line, the slope is 0. Okay, just to save us a little bit of work. And then lastly, we'll look at 5 to 7 seconds. So 5 to 7, I'll find my points. So 5 up here, 7 down here. You'll notice during that time, we have a negative slope. So I'll look at my points, 2 and negative 2. Okay, I'm going to come to a new page so we have a little more space to work. So at a time of 5 seconds, we have a velocity of 2 meters per second, just reading our points. And at a time of 7 seconds, we have a velocity of negative 2 meters per second. And now we're going to find the slope between those 2 points. So negative 2 minus 2, and 7 minus 5, y2 minus y1 over x2 minus x1. This gives me negative 4 meters per second. 7 minus 5 over 2 seconds. So negative 4 divided by 2, that should give us negative 2 meters per second squared. Okay, so now we have our acceleration during this time interval. Negative 2 meters per second squared. Negative because our slope is negative, and that means our velocity is going toward the negative direction. Okay, so now we have our last value here, for number 8. Number 9, the last question we'll cover in this video, says, how far does the object go during the time period 0 to 3 seconds? So we are asked for how far our object is going to move. That's really asking us something about our displacement, our delta x, or position. Right? Where are we located? How far are we moving? Now remember, if we want to know something about the position, and we have a graph of velocity, what that means is we need to find the area under our curve, from 0 seconds out to 3 seconds. So I'm going to come back to my curve, velocity versus time, and I'm going to look at from 0 all the way out to 3 seconds. So right in here, I'm going to draw a line straight down from a time of 3 seconds. So now, I'm going to break this up into two shapes. One's going to be a triangle here, okay, and then one's going to be a rectangle. So I'll first start with the triangle. Our area for a triangle, 1/2 base times height. That's going to be a base of 1 and a height of 1. So 1/2, base of 1 second, a height of 1 meter per second. So 1 times 1 gives me 1, times 1/2, so this is 0.5 meters. And then for my rectangle here, my area is just going to be, we could say base times height, or length times width, side times side. Either of those are appropriate. I've got a base of 1 second to 3 seconds, so that's a total of 2 seconds, and a height of 1 meter per second. So 2 times 1 gives me 2 meters. So my total area, I can add these together, 2 plus 0.5. My total area is 2.5 meters, which tells me how far I travel during that time interval. Now, we will be solving for question number 10 in our last video for the graphical kinematics practice. But remember, to find anything about the position, or how far we travel, which should be a 2.5, excuse me, we need to find the area under our curve, which tells us how far we travel during that interval of time. So again, depending on the graph we're dealing with, that's going to influence what we do with that graph. Because this is velocity versus time, we can read it directly to find velocity, using slope to find acceleration, or even using the area to find out our position. Hopefully this gets us started on most of the information with the velocity versus time graph. In our last video, we'll look at number 10. Good luck.